definition of average velocity, as we've seen, can give us this triangle. Definition of average acceleration can give us this triangle. The fact that a straight line v versus t graph implies that average velocities, the average of initial and final velocities, gives us this triangle. And of course, that's the condition of uniform acceleration. And there's a fourth triangle that really doesn't follow from any definitions except the definition of delta, which we should know perfectly well by now as change in. So it's very obvious that the change in velocity is the final velocity minus the initial velocity, but that does give us a fourth triangle that we kind of sneak in. And we've mentioned that before. Well, if we apply these definitions to get these triangles, and we should always be able to, first of all, know what the definitions are, and then be able to apply them rigorously from the very first part of the definition. Definition of average velocity is average rate of change of position with respect to clock time. This one is average rate of change of velocity with respect to clock time. And this is just a property of a straight line graph that's very obvious if you draw it out. Okay, well, in doing this, you end up with 7 quantities. You end up with V bar, delta S, and delta T here. Well, that would be V bar here, delta S, and delta T. What's added here? A bar and delta V. So we have, and we write A instead of A bar because of this condition. The slope of that graph is unchanging, so the acceleration is unchanging. So the average acceleration is always equal to the acceleration. We don't need the bar to indicate average in this case because of this assumption. Okay. Anyway, we add A to the list, and we already had delta T, but we didn't have delta V, so we add delta V. So now we have just about everything except V bar. And now if we list all the variables in these 3 triangles here, we have this list. Now I write 5 of them in a different color than the last 2. Okay, as it's going to turn out, these 5 are sufficient to define the motion of an object on an interval, provided the motion is uniformly accelerated. And these 2 are ancillary in the sense that when we're trying to reason out these relationships, we're going to use these 2. Also, we need these 2 for the scheme to work. The scheme being, pairing works when we're given any of these 8 situations. I'm not going to read them all to you. I'll read a couple and show you how we list these situations. By pairing, I mean, okay, well, let's look at the first situation. First situation is where we know the initial and final velocity and the change in position. So we know the first 3 of these quantities. If we know those, if we know these, well, we can pair up V0 and VF in a couple of ways. We can pair it here and get V bar, so now we know V bar. And we can pair up V0 and VF and get delta V in a very obvious way. So now we know V0, VF, and all these, and we also know delta S because we were given that at the beginning, and that leaves us only delta T and A to get. Note that we reason every one of those out by just pairing up 2 quantities. V0 with VF to get this, V0 with VF to get the delta V. Okay. Now, if we pair up delta S with V bar, we see that delta S is related to V bar. Well, if we pair up delta S and V bar, we have delta S and V bar, and that exists in a triangle with delta T, indicating, whether we think about exactly why or not, that these 2 quantities will give us this one. So now we're going to be able to find delta T. And then we know all the quantities except for A. Well, A is your delta V, involved with your delta V and delta T. We know delta V, we know delta T, just found it, and now we can determine A. So, in each of those lines of reasoning, we paired up 2 quantities in one of these triangles and found a 3rd quantity that we didn't know. That's a really good picture of the way these things relate. Now that doesn't give us all the insight we get when we actually apply the definition and understand just what the relationships are, but we've been there. So presumably we can do that, and if not, this is going to give us more practice. Now, I list all the sets of 3 quantities for which pairing works, for which, given any of these, we can pair up 2 of the quantities with at least one of these triangles and get something new that we aren't already given. And then we can take that information and do another pairing and get another thing and another thing and another thing, and at the end we have the 3 we were given plus the other 4. We know all 7. And we never have to think about anything more complex than how does this and this go together to give us something new. Okay, well, pairing works then when we're given any of these combinations. That's V0, VF, and delta S, V0, VF, and delta T, V0, VF, and A, V0, delta S, and delta T, V0, delta T, where are we? V0, delta T, and A, VF, delta S, and delta T, VF, delta T, and A, delta S, delta T, and A. Those are 8 possible combinations. There are only 10 possible combinations of these 5 quantities, the 5 quantities I've listed in blue here. And the other 2, pairing doesn't work. If you know V0, delta S, and A, doesn't work. If you know VF, delta S, and A, pairing doesn't work. There's something else we can do, and we'll see that soon enough. But let's get our hands on the pairing idea. Okay? Now, we do the example where we're given V0, VF, and delta T. I kind of pointed to what we do for V0, VF, and delta S, but I've written this out in more detail to show the entire process, including how we apply it if we're given a set of actual quantities. Okay, well, if we're given V0, VF, and delta T, the first thing we want to do is try to pair 2 of these. Okay, well, if we try to pair V0 and delta T, they don't appear in any of these triangles together. We can't use them. If we tried to pair VF and delta T, same thing. They don't appear together in any of these triangles, so they aren't related by this definition, by this definition, by the property of a straight line graph, or by the definition of delta. However, if we have V0 and VF, we're off to a very good start because we can pair V0 and VF to get V bar. And then we could pair V0 and VF as well to get delta V. So, let me grab a piece of chalk, hang on. Now, I already did my underlining when I did the long view of this, but we started with V0 and VF and delta T. And we combined V0 and VF to get what? Well, we combined it to get delta V here, we combined it to get V bar here. So now we know this, 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 and this. Okay, so I write that down. V0 and VF gives us V bar. We can see that. V0 and VF gives us delta V. We can see that that's going to be true. We'll think about what that means in a few minutes. Okay, but now, what can we do with what we now know? Remember, we don't yet know delta S and A. Okay? What can we combine? Well, we have all kinds of possibilities. And mainly, we can combine delta T with either of these 2, and if we combine it with each of these 2, we're going to be done. So what do we get if we combine delta T with, well, I did delta T with delta V first, yeah. Okay, so what do we get if we combine delta T with delta V? Well, what triangle does that put us in? From delta V and delta T, we can determine the acceleration. Okay, so we know this and this, therefore, we find the acceleration. Okay, what's left? Just delta S, but if we combine delta T with V bar, we have delta T here, V bar, and delta S in the same triangle, indicating that we can find delta S. So, V bar and delta T give us delta S. So, V0 and VF give us V bar by the 3rd triangle, and then by the 4th triangle that we kind of sneaked in here, we get delta V. And then delta T and delta V go together in the 2nd triangle to give us A. V bar and delta t go together in the first triangle to give us delta S. That tells us how we're going to be able to reason this out, but excuse me, it doesn't tell us exactly how the reasoning is going to go. So let's think that through. Okay, how do V naught and VF give us V bar? Well, V naught and VF give us V bar by the straight line V versus T graph, which tells us that V bar is the average of VF and V naught. That's the importance of the straight line graph. Okay, how do V naught and VF give us delta V? That one should be really obvious. Okay, delta means change in velocity. How would you get the change in velocity if you know the initial and the final velocity? You would subtract the initial from the final. So that's just by definition what delta means. Now, over here, we got to do a little more thinking. Okay, how do delta V and delta T and delta V give us A? Well, this comes, as we've noted up here, from the definition of average acceleration. And we have already thought through the definition of average acceleration and how it gives us this. If we start with the definition of average acceleration and do our reasoning, we find that the average acceleration is delta V over delta T. Average rate of change of velocity with respect to clock time is change in velocity divided by change in clock time, which we write by delta V over delta T. So, given delta T and delta V, we have the numbers to plug in here to get our acceleration. Okay, what about this one? Well, definition of average velocity, average rate of change of position with respect to clock time, by the average rate of change definition, that's change in position divided by change in clock time, and there we symbolize it. Okay, so V bar is delta S over delta T. We're given V bar and delta T. Does this do us any good? Yeah, we're given this and this. All we got to do is find this, multiply both sides by delta T, and there it's going to be. Working through an example where we know V naught, VF, and delta T. Let's say that V naught's 20 meters per second, VF 5 meters per second, delta T 3 seconds. We get V bar, just following the same order of reasoning that we had here. V bar is V naught plus VF over 2, as we just saw. That's 20 meters per second plus 5 meters per second over 2 comes out 12.5 meters per second. Delta V, second thing that we found here. Okay, delta V is just VF minus V naught, the obvious thing that doesn't really need a triangle, but and VF is 5 meters per second, V naught is 20 meters per second. Subtracting, we get negative 15 meters per second. The negative indicates that we're slowing down. If we start at 20, end up at 5, we're slowing down. Okay. Average acceleration comes out to be delta V over delta T, so we divide our delta V by our delta T, and we get negative 5 meters per second squared, in a very obvious calculation. And V bar is delta S over delta T. Well, we're going to go ahead and do the algebra. We multiply both sides by delta T. We get delta S equals V bar delta T. And V bar being 12.5 meters per second, as we found up here, we multiply that by the 3 seconds to get our 37.5 meters. The deeper understanding we get from this process is going to serve us well as we attempt to understand other things that go on in physics, which are not any more complicated than what we're seeing here. So once we develop the ability to reason and the ability to model, everything becomes much easier than it would otherwise be.